Okay, good morning.
So we start the lesson. So we continue the topic of infinite series with this topic, which is called geometric series. So geometric series is actually a very simple one. So if I have a series, for example, I start with a real number a, and every time I multiply my number, my term, with a constant fixed number r. For example, this is a, and then I multiply a by r, and then I multiply this by r, it becomes a r squared. I multiply this by r, it becomes a r cubed, and then I start adding them up. Okay? So what we see here is called a geometric series. And this number a, which is of course clear, the first term, and the fixed number r that I am multiplying to produce terms every time, it's a fixed number, and it's called the common ratio. And of course, if I want to write it in the form of sigma, as we are used to, so I write it as sigma a r to power n minus 1, and I go n from 1 to infinity. If I place 1 here, r to power 0 is 1, it generates the first one. If I put 2, it generates the second one, and I add them up. So this series is called the geometric series, yes? So we want to know if geometric series converges or diverges, or under what conditions it converges and under what conditions it diverges, okay? So let us review everything again from yesterday's lesson. Let us say that I give this duty to you and I want to see if this series converges or diverges. Do you remember what is the first thing we have to do? What was it? We need to set up a new sequence, which is called the sequence of partial sums, and look at the limits of that sequence of partial sums. Yes? So this means that I will define a new sequence little s sub n to be the sum of the first n terms, and then try to see if this new sequence has a limit or it doesn't have a limit. If it has a limit and the limit is L, I say that my series converges to L. If that limit does not exist, I can say that the series diverges, and if it goes to infinity, I can say my series diverges to infinity. Okay, so I have to calculate Sn. In the previous examples, all the examples we did was the case we could calculate Sn. Because what is Sn? Sn is the first term, plus the second term, plus the third term, until the nth term. So what is the nth term? Is a r to power n minus 1. So this is my Sn. Yes?
Isn't it AR squared?
What?
You missed one.
Yeah, yes, thank you. This is AS. Thanks. Okay, so this is Sn. And you see that when I write Sn, I have these 3 dots. Okay? Most of the time, it is not possible to find a closed formula for Sn. A closed formula means an expression which is equal to this without these 3 dots. But in this case, we can. Of course, in the previous cases, all examples I solved was telescopic sum, but this is not a telescopic sum. So the question is that, is there any way that I can find this sum in a closed form or not? In this case, the answer is again yes, but the technique is different from telescopic sum. Okay, so how should I do that? Let me see if I'm recording. Yes. Okay, so how should we do that? The technique is that, by the way, first of all, I am assuming that r is not 0. Okay, because if I put 0, then these terms will cancel out, and I'm left with one single. So, and then, of course, here, let us assume that r is not 1. Yes, let us assume that r is not 1. If r is not 1, I will discuss about what happens if r is 1. Because if r is 1, then I am not in big trouble. All the terms will be a plus a plus a, and it wouldn't be hard to discuss about the divergence or convergence of that series. Okay, but so let us assume that r is not 1. What I will do you have any idea how can I get rid of these 3 dots? You should have seen it in the high school. In high school, we do not have infinite series, we terminate somewhere, and it is called geometric progression. Okay, so that's the difference between geometric progression and geometric series. So if you want to find it, the technique is to multiply both sides by r. Then what happens, this becomes AR, the next one becomes AR squared, the next one becomes AR cubed, and this list continues AR to power n. Yes, but instead, let me write the last one here. So I'm multiplying this by an r, but I want to see what happens. If I reach to AR to the n, then the previous one is definitely this one. Yes, do you agree with me? I'm just multiplying both sides. Now, can you see what is going on now? I want to get rid of more, as many terms as possible. So it motivates me probably subtract these two. Yes, because if I subtract them, Sn minus Rsn becomes equal to what? So you multiply in your head this by a minus sign and add it to the upper one. So this becomes minus AR, will cancel that one. This will cancel that one. This will cancel the next one. This will cancel that one. So what are the two terms left? A is left from here. And then the last one with a negative sign, because I'm multiplying everything by a minus sign. So it becomes minus AR to the n. Yes? And then I am looking for Sn. So I factor Sn out from this relation. So it becomes 1 minus Rsn equals to, I factor an A out. And this is why I am assuming that r is not equal to 1, because I am looking for this question mark. I want to divide everything to by 1 minus r, so I need that r is not equal to 1. So if r is not equal to 1, then what happens, Sn that I am looking for is A times 1 minus r to the nth, 1 minus r. And this is an expression which is equal to Sn, but it is a closed form. It means that it doesn't include these three dots. So that's a formula for Sn. And this is the reason that I need r shouldn't be 1, because I want to divide by it. Okay, then the question is that I want to see if my series converges or diverges. So what I need to look at, I need to ask myself, what is the limit of Sn when n goes to infinity? Okay? And depending on the size of r, the answers will be different. For example, for the most important case, what happens if there are many things that I have written so we can see them. Yes? So these are all possibilities. Yes? So that you have for this. For example, let us consider that r, I want to calculate this limit. I consider some cases. One important case is that r is strictly between, so let me write it and ask your opinion about it. If r is between minus 1 and 1, okay? And I am asking you to take this limit when n goes to infinity. So there are a and r letters here, but they are not variable because n varies. So this is a constant number to power n, but I am assuming that my constant is between minus 1 and 1. Do you remember we had this theorem before? So what will be the limit of r to the n if r is between minus 1 and 1? 0. 0. So this becomes 0, so it will be a over 1 minus r. So you have to remember these formulas, or you need to know how to derive them. So it's a very important case. Okay. So then what happens if r is greater than 1? What happens if r is greater than 1? You can discuss these situations yourself. If r is greater than 1, what will be this limit? Infinity. This will be infinity. Because of that minus sign will be minus infinity. If a is positive, it becomes minus infinity. If a is negative, it becomes plus infinity. So if r is greater than 1, a is positive, then it becomes minus infinity. If r is greater than 1, a is negative, it diverges, by the way, you have to write it diverges to plus infinity. And then of course you can discuss about other situations. What do you think will happen for this r equals to 1 that I have excluded? Because this formula is only valid if r is equal to 1. But if r is not equal to 1. But if r is equal to 1, what happens? The term, this Sn becomes a plus a plus a plus a n times. So it becomes Na. Okay, and in that case, the series, so in that case, if r is 1, then Sn is nothing except Na. And if I ask you what is the limit of Sn, n goes to infinity, the answer will be again plus infinity if a is positive, minus infinity if a is negative, and 0 if a is 0. Yes? And the question is that what happens if r is less than minus 1? Again, if it is less than minus 1, or if it is minus 1, then this will diverge. But because this will oscillate, we just simply say diverge. I mean, these are all possibilities you have to know. So this is the most important case. If r is between minus 1 and 1, you know that geometric series converges, and you have to remember this number as its sum. Okay, is that clear? I have written all the cases here, but it is not hard to derive them yourself. Any questions? Okay. So remember, yes.
Maybe it's a typo in the notes, but the
In the notes?
greater than 0.
Yeah, please fix them if you see. Which one?
I just got the 3 and 4.
3 and 4. If r is 1,
the other way around on the a greater than or equal to 0, like greater than 0 or less than 0.
is
And
it?
it's got minus infinity.
If r is greater than, if r is 1,
No.
it is plus infinity if a is positive. So for equality of 1, it is correct. But if r is greater than 1, what happens? It might be you are right. If r is greater than 1,
I don't know, I just put as...
no, I have put minus infinity here, yes. Might be that is wrong, yes?
Yeah.
Yes, I have to, so... No, r is greater than 1, a is positive, diverges to plus infinity. Oh, yes, no, that is correct.
Okay.
Yeah, do you know why? I was a little bit careless. You see, thank you very much for pointing out. Because if r is greater than 1, the denominator also becomes negative. I didn't consider this negative here. So that one that I have written is correct, not this one. Thank you very much for pointing out. So if r is greater than 1, let us check it again. If r is greater than 1, the limit of this one becomes infinity. So the numerator becomes minus infinity. And the denominator also becomes a negative number. So far it is positive infinity. So this means that if a is positive, this is positive, and if a, thank you very much. Yes, thanks. Okay. Now let us go to these examples. Yeah, let us try to do as many of them because these are simple. So somehow you need to train your eyes to catch this geometric series pattern. Okay, so let us, for example, start with the first one. Oops. Yes, so we have this sigma n goes from 2, yes, I cannot see that, n goes from 2 up to infinity, and then I have minus 5 to the n divided by 8 to the power of 2n. Okay, so what is the question? The question is determine whether the following series are convergent. If they are, find their sum. Whenever you see that they are asking about the sum, either it should be a telescopic sum at the end, or it should be geometric series for the time being. Okay? So how should I know if this is a geometric series or not? You don't have to fix this into this general formula. My advice for you is to write some of the terms. Okay, for example, the first one starts from 2. So if I put 2 here, so it becomes minus 5 to power 2. Don't do the calculations. I just want you to do it just nominally. So if I put 2 here, it becomes 4. Do you agree? This is my first term. Let me choose n, the next one, 3. This becomes minus 5 to the power of 3. And this becomes 8 to which power? If instead of n I put 3, it becomes 8 to power 6. If you are convinced, okay. If not, do one more. So if I put 4, it becomes minus 5 to power 4. And then I have 8 to power 8, and this will continue. Now, can you see this is a geometric sum? The geometric sum starts somewhere, but the point is that every time it should be multiplied by a fixed number. For example, if I ask you which number is that, so that this is multiplied and give me this one. You see, the number that I have multiplied here to generate this one, I have to add 1 power of minus 5, so minus 5 should be multiplied, and I should add 2 powers of 8. So do you agree with me? If I multiply this expression by this number by that one, I get this one. Do you agree? And then the same story happens here. If I multiply this one by the same constant, that's important. It should be the same constant. I will generate the next one. Yes? And this pattern will continue. Yes, do you agree? So it is a geometric sum. So is this geometric sum convergent or divergent? So this is my R is minus 5 over 8 to power 2, which is 64. And I know that this is less than 1, definitely, and it is greater than minus 1. So the series converges. 2, I have to remember the formula. To which number? This number. A is the first term, which in this case is 25 over, it's a very big number. So let me write it like that, 25 over 8 to power 4. Let us see if we can get rid of this number somehow. And then 1 minus this number. There's nothing we can do that much, so if I simplify this, so it becomes 69 over 64. This will be 64 to power 2, 25. Nothing that much I can simplify, so it is 25 over 64 times 69. That's it, whatever that number is. Okay, so let us do the next one. The next one is sigma. This time n goes from 0 up to infinity. And then I have 2 to the n plus 3. And then divided by e to the power of n minus 3. So you have to train your eye, as I told you, to see that this is indeed a geometric series. Is it? So let us test. If I put 0, what happens? It becomes 2 to power 3 e to power minus 3. If I put 1, then it becomes 2 to power 4 divided by e to power minus 2. If I put 2, it becomes 2 to power 5 e to power minus 1, and it continues. So it starts from somewhere, but the point is that every time I am multiplying the previous term by the fixed constant, what that constant is here, this is multiplied by 1, 2, and 1e. Do you agree? If I multiply this expression by 2 over e, 2 to power 3 becomes 2 to power 4, e to power minus 3 becomes e to power minus 2. But this is not enough. We have to convince ourselves that this pattern continues exactly the same. Do you agree that if I multiply this one by this expression, by the same expression, I will get the next one? The answer is yes. So this means that this is a geometric series whose R is 2 over e. Yes? Is this convergent or not? Yes, because this is also between 1 and minus 1. So the geometric series, so this will imply that the geometric series, the series converges to A, the first term, which is this number, 2 to power 3 divided by e to power minus 3 divided by 1 minus r. Yeah, you can simplify it yourself. This is a very simple test. What about the next one? For example, the next one is a good question. Might be it's a slight deviation from the pattern of a geometric series, yes? So, do you think it's a geometric series or not? So I have pi, the famous pi number, to the power of n over 2, but I have cosine n pi, and n goes from 1 to infinity. So what do you think here? So if you want to follow the same idea, because you have some power of n on a fixed number, by the way, what is the general pattern? In all these cases, I have a constant number in the base, and I have some power n on top. So this should be somehow comparable to this one. If you know from your high school studies, so what is cosine n pi? You know that n is an integer, 1, 2, 3, 4, etc. So it means that n can be even or odd. If it is odd, it will be pi, 3 pi, 5 pi, etc. Cosine of all those numbers are minus 1. And if n is even, 2 pi, 4 pi, 6 pi, all of them are 1. So this is a good thing to know. Cosine n pi is equal to 1 if n is even, and it is minus 1 if n is odd. Instead of writing it in two expressions, I can simply compactly write it as minus 1 to power n. Yes? Because if n is even, minus 1 to power even becomes 1. And if n is odd, minus 1 to power an odd, it's minus 1. So it's a very nice formula. Cosine n pi is another name for minus 1 to power n. Yes? So instead of this one, I can write it as sigma n goes from 1 to infinity, pi to the power of n over 2 times minus 1 to power n. Okay, so then you can open it up. Again, what is the motivation that it might be a geometric series? Because I have constant numbers and then raised to some power which depends on n. If this is the case, this is more or less an indication that it might be a geometric series. Okay, so if I put 1, it becomes minus pi over 1 over 2. If I put 2, it becomes positive pi. If I put 3, it becomes negative pi over to the power of 3 plus 3 over 2, and etc. So do you think it's a geometric series? What is the common ratio, which is r? Here, if I want to go from here to here, I have to multiply by a minus pi to power 1/2. Do you agree?
Yes.
But again, the point is that if I multiply this by the same constant, I will go to the next one. So it is. So this means that this is a geometric sum where r is minus square root of pi to power 1/2. And I hope that you agree. This is definitely less than 1. And is it or not? Yeah, it is. But is it bigger? That so it's minus square root of 3. So it is minus 1 here. Yes. So square root of pi is 3 something. Square root of pi is definitely greater than 1. So when I raise, okay, so it will be somewhere here. Do you agree?
Yes.
So is it divergent? So this is divergent. It's not convergent. So let me just change it. So this is less than minus 1. So the series diverges. But can I say diverges to where? If r is less than minus 1, you have it on the board or not. If r is less than minus 1 and a is not 0, the only thing I can say is I can say it diverges. Yes? The series diverges. Yes? What about the last one? The last one is very simple. 1 minus 1, 1 minus 1. Because some people would say that, okay, 1 minus 1 is 0, 1 minus 1 is 0, 1 minus 1 is 0. So then the sum should be 0. Okay? But this is a geometric sum. Yes? So this 1 minus 1 plus 1 minus 1 plus 1 minus 1 is a geometric sum. Can you see that? So it's a geometric sum, but what is the common ratio? The common ratio is minus 1. Okay, so it cannot converge. So the common ratio is minus 1 and A is not equal to 0. So it diverges. Yes? Okay, so that was very simple. Now let us see what we have here. These are two important formulas you need to know about them. For example, let me ask you about this. If I write 1, if x is a number whose absolute value is less than 1. Okay, this is a very famous sum. If I write 1 plus x squared plus x cubed, and I continue this list forever, if absolute value of x is less than 1, do you see it is a geometric sum? Yes? So, and this, what is the first term? The first term is 1, and what is the common ratio? Every time I am multiplying the previous term by x. And I myself assume that the absolute value of x is less than 1. In other words, this means that x is between minus 1 and 1. So now my question, do you think that this series converges? The answer is yes, because the common ratio, according to my assumption, is between minus 1 and 1. So this converges, and what is its sum? Its sum uses this formula. The first term divided by 1 minus the common ratio. The first term in this case is 1 divided by 1 minus the common ratio. It's a very, very handy formula. So if you have an x which is strictly between minus 1 and 1, this sum, this infinite sum can be replaced by this compact formula 1 over 1 minus x. And what do you think about this? Do you see that this is also a geometric sum under the same constraint? X is between minus 1 and 1. So what is the first term? The first term is 1, but what is the common ratio in this case? Minus x. If x is between minus 1 and 1, minus x is also between minus 1 and 1. So this series also converges. Converges to what? To the first term, divided by 1 minus the common ratio. But 1 minus minus x becomes 1 plus x. But be careful, that's extremely important. These two formulas are only valid if the number x you choose and put this in this formula is somewhere strictly between minus 1 and... Okay. Now, more or less, we have to give up and see that if the series are convergent or divergent without having the sum. Okay, so very similar to the improper integrals. But before that, this is a very important theorem. So let us go through it together. This theorem tells you that if you have two infinite series and you know that both of them converge, one of them converges to A, capital A, one of them converges to capital B. If you multiply all the terms of the first one by a constant c, the effect of this action is that you multiply the sum by a c. It's very normal and natural. And the other one is also very natural. So if you have the sum over a, the first one, plus or minus the second one, you can write a plus or minus b. So the sum, the sigma of the sum will be the sum of the sigmas, or the difference the same. And if you know that all the terms an are less than or equal to bn, then you can conclude the sum is also less than the sum of the second one. Okay, and now why this is good? Sometimes it is good to actually solve some problems. For example, let us solve one of these problems. what is your opinion about this? Find the sum of each of the following series. So sigma so let me write here. Sigma n goes from 0 to infinity. And then what do you have? You have 3 plus 2 to the n divided by 3 to the n plus 2. Okay, so this series, what is your suspicion about what type of series you are suspecting here?
Geometry.
Geometric, but it is not geometric. Yes? If you start doing it, for example, if you put 0, what do you get? You get 3 plus 2 to the power of 0, which is 1, divided by 3 to the power of 2, which is 9. Okay, so the first one, let me write it here. The first one is 4 over 9. What is the second one? If I put 1, it becomes 5, and then this becomes 27. Yes? If I put, I don't know, 2, it becomes 7, and then it becomes 81. Do you see that this list is not a geometric list? Even though the denominator is always being multiplied by the same constant 3, but 4 turns to 5, 5 turns to 7, and etc. Okay? So it's not a geometric sum, but your hunch is actually correct. But it is not one geometric sum. You can split it into 2 geometric sum, and then you have to write it properly that people, when correcting your paper, understand that you understand everything. So you can do it like this. You can say that, okay, 3 plus 2 to the n divided by 3 to the n plus 2 can be broken into this form. Yes, do you agree? Here you can simplify a little bit. It's 1 over 3 to the n plus 1. And here you can just write it as it is. So this expression can be broken into 2 parts. But now can you see that each part individually is a geometric sum? Yes? So if I increase n, every time the numerator is constant, I am adding a factor of 3 to the denominator. So this is always being multiplied by 1 over 3. Yes? And now this one, if I increase n, every time I am adding 1, 2 to the numerator, 1 factor of 2 to the numerator, and 1 factor of 3 to the denominator. So the common ratio here is what? So I would say that when you do this, and then you have to write this, we consider, if you want to write it properly, we consider sigma, the first one is 1 over 3 to the n plus 1, n goes from 0 to infinity, and sigma, n goes from 0 to infinity, the other one is 2 to the n divided by 3 to the n plus 2. We consider these two. Both of them are geometric series. Yes. The first one, can you tell me what is the first term in the first one? I put 0. It becomes 1 over 3. And can you tell me what is R1 for the first one? Every time I am multiplying it by 1 over 3. And this one converges, because it is between minus 1 and 1. So this converges to what? To A divided by 1 minus R, which is 1 over 2. And then this one, A1, A2, let me write it here. So the first term of the second one, if I put 0, it becomes 1 over 9. And can you tell me what is the common ratio here for the second one? Are you following what I'm saying? Okay, so what is R2 now? What is the common ratio for the second one?
Is it 2 by 9?
2, no, 2 by 3. Because if every time you increase 1 power for 2, 1 power for 3.
Oh,
So it is not 9. So it is 2 over 3. Are you with me or not?
yes.
Okay. And then is it convergent? Again, yes. It converges to what? It converges to 1 over 9, 1 minus 2/3. And if you multiply by 9, you get 1, 9 minus 6, 3. Am I right? Yes. So this means that therefore, the original series converges to, okay, can you complete it? Converges to what?
5 over 6.
Is we add them, thank you. 1 over 2 plus 1 over 3, which is 5 over 6. So sometimes you have to split your series into the sum of, but you have to defend. Don't say, in exam you shouldn't write that this sigma is equal to the sigma of the first one plus the sigma of the second one. In principle, you have to convince yourself that each one of them individually converges, and then you can go and say that, okay, now that I am sure that it converges, I can use this formula. Okay, somehow like this. So for example, let us do one more. Sigma n goes from 1 up to what? Infinity. And then I have 1 over n times n plus 2. So they have asked you to find the sum. Yes, they are asking you to find the sum. So this means that we should be able to you should be able to find S sub n. And clearly this S sub n is not geometric one. So there's only one more other method that you know. What is that?
You split partial fraction and then do
Yes, the telescopic sum. But there is one problem here in the telescopic sum because the sum is not really telescopic. You have to modify that. Okay, so let us do that. So what we do first, I would write Sn. Sn is the same sigma. I would change my counter to k, and I go from 1 to this n, and I have 1 over k times k plus 2. As you said, I would write it as partial fractions, 1 over k, k plus 2, so I have write a over k, and then plus b over k plus 2, and I will try to find a and b. But this is so simple we can guess, yes? So if a is 1 over 2, if you cannot guess, of course you can do it the normal way, and that b is minus 1 over 2. Yes? So if I do that, then this means that, therefore, 1 over k times k plus 2 becomes equal 1 over 2 minus 1 over 2. So if you don't mind, let me factor 1 over 2 out. Yes? Okay, so this means my Sn will be equal to the sigma of this expression, but 1 over 2 is constant, so let me pull it out. And then I have sigma 1 over k minus 1 over k plus 2. And then what I have k goes from 1 to n. Okay, but you see this is not a telescopic sum. Why? Even though that's good, I have two expressions with a difference in between, but if I change k to k plus 1, it will not generate the next one. For telescopic sum, I need my counter differ by exactly 1. Okay, so I have to modify a little bit. It is not telescopic sum, but it is not hard to see what to do. Can you see that? You need to add something, subtract the same thing, so that you can modify it into two telescopic sums. Yeah, so what can I do by this hint? I can write 1 over 2 sigma k goes from 1 to n, and I would write 1 over k minus 1 over k plus 1, but I cannot just write it there unless I add the same expression. And then I will copy and paste the last term. Do you agree that I haven't done something wrong? I have subtracted and added the same thing. So this is legal, that is completely true. But why this is beneficial? Because I can split this sigma into two sigmas, and this is a finite sum. I don't need even to discuss in this form. So what I will do, I would write it as the sigma, k goes from 1 to n of the first part, plus sigma of the second part. Are you following what I'm doing? Here you don't need to justify. Why? Because you see that when the top one is finite, this is always true. No one will ask you why. I can split them. And this is not infinity, this is just simply n. But do you see this is a telescopic sum? This is also a telescopic sum. Because here if I change k to k plus 1, this will generate the next term. Here if I change k to k plus 1, this will generate the second term. So both of them are telescopic sums. Do you remember what I told you about the sum of telescopic sums? What is the answer to this one? You have to replace these k's with these values. For the so the smaller value go to the one with lower counter. So this k will be replaced here, and this upper one will go here. And the same story here. The lower one go for the term with the lower value of the counter. So it becomes 2, and then n goes there. This is your Sn. So therefore, Sn is equal to this closed form. Yes, and then I take the limit. So the limit of Sn, n goes to infinity. What happens here? This becomes 0, and this becomes 0, so it becomes 1 over 2, 1 plus 1 over 2, so it becomes 3/4. And by the way, if someone asks you, did we use this theorem? So I will modify this. I will probably put one of these examples backward, because it doesn't use this theorem at all. What I am doing, I have written Sn. Sn is just a normal sum, and a normal sum, I can split the normal sum always, and split it into two telescopic sums and find the answer. So sorry for that, I have to modify this. This is not related to this theorem. I thought that we had to use this theorem.
Not just do this without mentioning any theorem because of some commutativity.
Yes, exactly. Because there is, you see what I have done, this example could be done yesterday. It has nothing to do with this theorem. Yes? Because I am working with finitely many sums. Okay, so if you don't mind, let me jump this one. I will come back to this after the break, but let us do this one. Because I told you, do you remember? I told you that this is always true, but don't think that this is always true. A natural question is that, can you give me an example that shows that this is not in general true? Yes? Do you have this in mind? Yes?
If you just have sum of an, where an is just like 1, 2, 3, 4, 5, 6, so then it instead keeps diverging. So if an is just n, and then bn is also like n by 2 or something, then both of them approach infinity. Or bn can be anything, but if an is diverging...
No, I mean, you need to give an example so that this equality does not hold if one or two, both series diverge. Yes? So that example that you... it doesn't show anything. Yes? So for example, if I give you this series, do you remember what was the name of this series? So let me write it here for you. So if I consider this series 1 over n, do you remember what was the name of this series?
Harmonic.
Harmonic series. Was it convergent or divergent? It was divergent. According to this one part of this theorem, of course you have to rely on your intuition here as well. What can you say about this series?
Also divergent.
Also divergent. Okay, but now if I add them up, what will happen? If I add this to this one, yes, you know the answer to this without any calculation. What is this sum? Do you think that this series converges or diverges?
0.
It converges to 0 because all the terms are exactly 0. So this is 0. The left hand side is 0, but the right hand side is meaningless. It is infinity minus infinity. but they are not the same. Infinity minus infinity is not the same as 0. So for using this theorem, you really have to make sure that those series involved, all of them are convergent, and if you want, then you can split them, not before. Okay, so let us have a break for 5 minutes now, and then we come back to the other parts.